Hello, everyone. I'm Ray No, Core77 Senior Editor. Thank you for joining us for this month's Core77 Crash Course on how to design and 3D print flexures. Today's presenter is Akaki Kuumeri, and if you signed up for this, you've probably already seen his YouTube channel where his video on using the one-handed PlayStation controller he designed got, I think, 8.2 million views. Now, using a 3D printer to make flexures is a fairly new phenomenon, and Akaki is the closest thing to an expert on the topic. He spent a lot of time designing, printing, testing, and experimenting with flexures, and he's developed a lot of useful information that's going to help you design and print your own. In this presentation, Akagi is going to run you through the basics of flexures, including the fact that 3D printers are actually not the ideal way to make flexures. But stick with this through the end of the presentation because Akagi is going to show you all of the practical tips, tricks, and workarounds he's come up with to avoid the downsides of using a 3D printer. Now, because we're in very different time zones, Akaki has pre-recorded this presentation, but he is going to tune in live at the end to field your questions in the Q&A. So please get your questions loaded up in that chat window, and after the presentation, we'll take the best of the best and have Akaki answer them. Okay, producer, if you could please cue up the presentation.
All right, hello everyone, and welcome to my presentation about 3D printed flexures. My name is Akaki, and I don't want to be on camera today, so I'm going to put my camera down onto my workbench. And today I will come to you as a pair of talking hands, if that's okay with you. Today's outline. I'm going to tell you very briefly what flexures are, and show you a ton of examples of these. I have a box full of interesting trinkets you might like, and I'm going to ask the question if you can 3D print these. And spoiler alert, it's not the perfect technology for 3D printing, so I'm going to show you why not. But there are ways around it. So at the end, we'll show you a few of the learnings and tricks that I have that will let you use this flexure technology as it applies to 3D printing. All right, so my name is Akaki. I have a few 3D printers at home. Originally studied computer science and engineering, so I have a little bit of CAD experience, but mostly I'm self-taught. I like flight simulators, especially Condor 2 for gliders, if you want to play with me one day. And I love building different sort of controllers and control interfaces. You might have seen my 3D printed controller designs that use flexures, such as this joystick online. All right, let's get started. Thank you for coming. And here's my presentation. Okay, it starts with this. To get a little taste of what flexures are as it comes to comparing them to older, more traditional technologies, take a look at this. This design I've found on Prusa printers. I will have the link to whoever made this. I'm sorry, I forget the name, but it's a pen holder for your printer, so you can attach a pen to your printer, put a piece of paper down on the print bed, and suddenly your Prusa printer, your Prusa Mini here, is a pen plotter. And I've printed a copy of this attachment here. So this is the files that you get. This would, with the round hole there, screw onto your print head. And here you have sort of a linear rail, because once you have a pen on here, like so, you want to give it some room to slide up in case the printer pushes too hard down on that paper. And to give the slider a little bit of positive loading, you add a rubber band around it. So now you have a linear rail and a elastic, a spring. And this completes your pen plotter. So if my hand was the print bed, if my hand was the print head, you could make it draw plots like this without scratching the print surface. Now, I've made my own version of this design. Sorry, I don't want to put down the original designer, but I've designed the same mechanism using flexures. Finally, we're getting to the meat of today's presentation. So here is a flexure pen holder for your printer. It's a bit larger, but it does the same function. Here's the screw hole. You would screw it onto your print head like that, move it around, and your pen clips on here. So it's a flexure that replicates the functions of a linear rail and a rubber band elastic spring at the same time. See? All right, sorry to whoever designed this design. I don't want to put you down. All right, that's the warm-up. What is a flexure? Very briefly. It's a related term to compliant design. Now, compliant design is opposed to the traditional mechanism design. So a mechanism is a collection of rigid parts. You have your bolts, your arms, and then to make a moving mechanism, you add axles, so pins and screws and bolts that your parts might turn around, rotate around. I have here is my one-handed controller, and it has hinges. Do not confuse this. This is not flexures yet. I'll get to flexures later. So this is the traditional sort of design that you might be used to. Now, compliant design. Finally, we're getting some examples. Here is something I found online. It's a compliant grabber mechanism. So if you push and pull here, these two jaws, they close in because of all these bendy bits. So this mechanism doesn't use only rigid parts, and it doesn't use any fittings or axles or bolts. Everything is one piece, but it embraces the flexibility of the material. So in traditional design, you will try and minimize bend. You add material, you add infill in your 3D print, and you add more steel and wood in your traditional sort of design until you get it completely rigid so you can understand and design it better. But in compliant design, you design around the idea of embracing this flexibility. Flexure, very related to compliant design. It's a subset of what compliant design. It's one element of compliant design. It stands for flexible structure. It's a part that's designed to flex, but also work as a structure. More rigidly, it flexes in one axis, but is rigid in another. So my little pen holder here flexes in this axis. In fact, it moves linearly in this axis, but you won't be able to twist it or bend it any other way. So it's giving structure, it's limiting the movement to pen to this one axis, but giving it freedom in another. That's a flexure. And often they manifest themselves in these flat flaps, like this tic-tac box lid here. So you've seen this, it will open and close because of that living hinge. So it's a thin piece of plastic that opens and closes. Here's another example of a flexure, a very old car suspension. Those leaf springs are designed not to move sideways, but bend under the load in one direction only. The first three pictures are more common flexures, but when it comes to the study and research on flexures, often you'll find this sort of micro positioning, or is it called nano positioning machines. So in very microscopic sort of equipment where you're moving nanometers to position a needle inside a stem cell or whatever. Advantages of flexures: there's no moving parts, and because of that there's no slop. So when you're making a mechanism with multiple hinges, axes, and bolts, springs, all these parts out of the more traditional sort of design regime, every single time you have parts rotating around each other, you will introduce a bit of slop, because the tolerances, they can't ever be perfect, can they? Relatedly, nowhere. And because there's less parts, there's less assembly. So this pen holder is print in place. You can take it off your print bed and it's a ready mechanism, where the previous version was 2 parts plus the elastic. No assembly. Disadvantages. They're not easy to design because our design principles, our CAD software, and everything we learn about mechanisms and designing mechanical things is based on this older sort of design, where you're only using rigid objects. Your flexures and compliant design, you never can have a continuous rotation or a large displacement of movement. So that's why it's called, that's why I have limited movement on there. And finally, you have something called creep. So this is material fatigue. You can never have a plastic 3D printed part like this under constant deformation without it fatiguing over time. I'll talk a bit more about that later. Now, before you get bored, I'll show you a bunch of these flexures that I've brought to you today. Some of these are mine and some of these are from different users online. I have no idea what this machine does, but it's very satisfying. You can see that these thin pieces all over the design work as springs, but they also work as the linear motion for these little springs here that advance the gears. Very cool. You've seen the grippers. Pull here and the grippers grip very slightly. I think this design is designed for that sort of metal manufacturing instead of 3D printing. Here, I love this. If you didn't know what was underneath this plate here, what would you guess? Would you think that there would be perhaps a spring that this rests on? Well, if it's a spring, you'd think that you could then rotate this table, but it turns out it's very free to move in X and Y directions, but you can't actually rotate it very much. It's very difficult to twist it. Well, could it then be 2 linear rails? So you have one linear rail this way and one the other way, both with their centering springs? Perhaps you could have that, but the answer is a ton of flexures. Do you see? This is a model of those microscopic nano positioning mechanisms that you use in very accurate science, but it's more of like a desk toy that you can print. Finally, we get to my own designs. I'm pretty proud of this one. So move the joystick around and watch closely. The joystick is on a ball joint sort of base there, and this black member, this is rigid, but it's mounted on 2 flexures, one on the y-axis and one on the x-axis, that allow this black arm here to move in 2 axes, much in the same way as this platform is moving, where it won't twist around like this, but it's free to move in X and Y, and that results in this end and this end performing the same motion. So if I turn this joystick in a circle, the thumbstick moves in a circle. I told you a lie. I told you that there was a ball joint under the joystick, but that's not true. You actually have more flexures. See how that part there is supported on these thin strips. That allows you to move it up and down. And further, this axis is the same. So If you can see inside there, you have this crossing. Here is a whole bunch of flexures in my giant Joy-Con. I call it the Giant Con. Can you guess what the mechanism inside might be? Look, it's a centered spring. There's spring-loaded buttons all over, and even the opening mechanism is a springy button. Wow, this is just flexures galore, isn't it? So let me take that off so you can see it better. Just to open it up, here's your first flexure. A very common clasp sort of design. The button is also spring-loaded with a flexure. Not very visible. These shoulder buttons, that's a flexure. Here the large, perhaps 5mm travel of the button is translated to only half that because of this mechanical advantage. So that end that is designed to push down on the same button on the real controller that mounts down here. That reduction in travel is achieved with this lever sort of flexure, and same on the other side. Here we go even further, where this stick, as it moves this black ring around, those motions are copied over to the stick on the real controller. And again, we can find the same mechanism there, where you have these two parallel lines and these two parallel lines forming a XY flexure. And further, the shoulder buttons also supported on these linear motion flexures, and they allow you to push down on the controller. Why I wanted to show you, oh, more flexures, look, these buttons also, they are held in place by their own springs. That's what a flexure is. It's a structure that's also a spring. Why I wanted to show you this, I don't just want to brag about my cool designs. The reason I wanted to show you is because I have the same design before I learned to think with portals, to think with these flexures. So here's, I forgot how to open this. There we are. Oh no. See, to make the same mechanism before I discovered the beauty of flexure design, I used, look, metallic springs, pins, and rigid mechanisms. More springs here, and the stick centering was also a elastic band. Compare the simplicity here. See? I'm gonna tell you, oh no, I'm never gonna see that spring again. I'm gonna tell you all about it. Alright, that was the fun part. Now let's go back to the theory part. So there's tons of resources out there for flexures and compliant design out there, but can I use these designs in 3D printing? And unfortunately, the answer is kind of. I have bad news for you, which is our household FDM 3D printers and our plastics that we use, they don't make very good flexures. PLA, the plastic that we use, and other common plastics that are in use, they yield too easily. So what is yielding? Here's a piece of our common PLA filament. You know that you can bend it around up to a certain degree. That's fine, but at one point some of these plastics, they start getting white. You've seen this, right? See? That has yielded. You've bent it too far and now it doesn't spring back anymore. Next, and this is perhaps even worse, our 3D printed plastics, they experience creep. Here's my test specimen that I've made. I make this for different materials. This is made out of PLA+, and this dial indicator here, you choose your favorite angle here. You choose how far to push it. I've left it bent like this since this morning, and now we can see where it likes to rest. So I'm gonna take this off. Look, it started straight, and now it's been left at this position, and it only comes back so far. This is the largest problem that we have. Yielding and creeping are the biggest problems with our 3D printed plastics. Here's a torsional spring, a little catapult you can make. You can't leave this loaded for a long time, but it's fine as a nice desk toy that only gets loaded before it's used. That's fine, but not leaving it loaded. And finally, this is a bit more complex of an issue. Our 3D printed parts are not isomorphic. I've learned that word recently, and it means that they have grain, basically. If you're printing a flexure, let's say it's one of these flexures where it thins down, yeah, like here, or like in this toggle switch, where the more thick piece gets thinned down to a very thin spot. Well, if you're cutting this out of aluminum, or if you're cutting it out of Delrin, then this whole part will be quite isomorphic. So the grains and the fibers, or whatever it's made out of, will be in all directions, and it'll be equally strong no matter where you look. So you can, as you make it thinner, you can trust it to be quite strong here, then less strong, more easily bendable here, and then stronger again, right? As a function of the thickness of this part. But now if you're 3D printing it, you have to make it out of sausages. So you'll have the surface sausage here, you'll have another surface sausage there. What happens inside here? Well, you'll get a surface sausage up to here, but then that sausage has to turn around, and it'll make something like this, leave a gap there, right? So you'll start to see where this area of the flexure might be as strong as 2 strands of filament, whatever that means. But here it's no longer a linear, or I should say no longer a continuous function of strength as you go up the neck of this flexure, because the number of sausages changes but in steps, and it's even more complicated because of the different ways the infill might go. And for this reason it's very difficult to predict or simulate. But those are the challenges that we have for FDM printing flexures, but I do think there are ways around those. And I think there's a few reasons why, limited as they are, flexures with 3D printing are also a good match. And here they are. First, 3D printed mechanisms are quite often ephemeral. That's a word I learned recently. It means short-lived. So we can all admit it. We're making trinkets often, or we're making toys for our game consoles. Maybe Sony wouldn't make their own joystick attachments, their official joystick attachments with flexures, because you'll never know how long these are going to last, or the quality issues might be difficult. But for us hobbyists, making little one-off toys, little one-off trinkets, little patches and hacks, I think flexures are a perfect fit, because they don't have to be so long-lived and reliable. Next row there is an answer to the difficulty in analysis and design. Well, this whole field of tech, 3D printing, is all about rapid prototyping. So I think we can overcome the challenges in difficulty of design of flexures, because we can turn over prototype very fast. So we can do trial and error design. And down there, next row is what actually gives you a bit of a bonus when doing flexures over more traditional rigid mechanism design, is because 3D printing can produce very complex shapes that wouldn't be possible when carving or injection molding. You can suddenly make flexures in one piece that would be multiple pieces if you tried to make the same mechanism out of discrete parts. And finally, everything built in one part, there is no imprecision there, because there's no need for tolerance, there's no slop, because it's one piece. So, the last slide and this slide, hopefully they might cancel each other out, don't you think? Here, finally, we get to what I've learned over about a year of tinkering with 3D printing flexure designs. This is my flexure primitive, and all these designs are built out of this. And it's a 40 millimeter long wall, printed horizontally, so like this on your print bed instead of this. It's 0.75 millimeters thick and at least 10 millimeters wide as a band. That's it. That's my primitive. I'll show you the process where I got to this, because this is the perfect length, thickness and width that has been shown to work. It's not very scientific, but as I told you, unfortunately with FDM printed flexures, it's not very easy to scientifically analyze. Okay. Here is the process that I used to arrive at my flexure primitive. Here, thickness. Let me show you different thicknesses. So here is a thick with 2 C's flexure primitive. It's the same dimensions in other dimensions, but it's thicker. And then I have a very thin one as well. And the funny thing about the thin one is that it's almost impossible to print. Here is a 0.4 millimeter flexure, and you can start to see why my primitive is the correct Goldilocks size, because the printer actually can't print very much thinner. And the thicker, here you're losing a lot of that bendiness. It might work if it's longer and so on, but you also get back to that isomorphism issue. So why not one line? Well, this is what happens when you try to slice a one-lined flexure. The printer doesn't know where to start that wall, so it starts it all over between these two boxes. And you get this weak spot here where the line starts. Whereas if you have two walls, especially with these fillets like this, the outer wall of this box blends into this flexure line, and you don't have a stop there. Width, at least 10 millimeters in my testing. Here is a 5 millimeter wide flexure of the same dimensions, but see, you can twist it too easily. That's the reason. It can be thicker as well, but at least 10 millimeters, please. Length, 4 millimeters. I found this to be the perfect length. If you make it shorter, it doesn't want to bend in the center. It'll concentrate on some weak spots on the length, and you don't get enough travel either, because PLA is too easy to yield. 4 millimeters, I found it to be best. If you make it too long, now you run into the issue where if you have compression from the two ends, you can get a buckling in the middle. That's the reason. And finally, And this is sort of a limitation too. You might think that you'll be able to print flexures lying down like this, and this in fact was printed on the print bed. But there's no way to ensure that the print lines are longitudinal along this flexure, which is the strongest way to do it. Instead, this is now filled in like this, which is not perfect. And it isn't as stiff either. So please print your flexures standing up. It'll be the cleanest and the strongest. It's well known that 3D printing FDM prints are the strongest along these layers. Here we get to the fun part where we can start building up mechanisms from our primitive, our flexure primitive. So to make a simple hinge, well, you just use a single flexure. That's already a hinge for you. It only bends perhaps 10 millimeters at the end, but that's a hinge. If you want a more advanced hinge, use this X configuration. Look, this has the advantage that it's almost equivalent to turning around a fixed point, whereas the simple hinge, you can get some parallel movement like this. So this is the twisting, but this is the parallel movement. Whereas with the X hinge, I'm trying to do it parallel like this, but you simply cannot get it to move. It's totally solid, but it's free to move rotationally. This is what I've used in the joystick. This is the base of the joystick if you're interested to see this. There's two of these X hinges. Next, for linear movement, and I've used this a lot also, it's just two parallel lines. You've seen it here. I have a specimen here. This stays put, but I can move the other end about 5 millimeters both ways. You can have a more linear motion with two of these stages. So here's two parallel lines, as you've seen in the original. That's the same piece there. They twist so, but these two other parallel lines are here to, let me turn it this way, are here to cancel the up and down movement. So now as I move it backwards, back and forth, this shuttle, this moving piece, not only does it have double the horizontal movement, but it moves vertically no longer. The distance here is constant. Combine these and you get the XY movement. I've used this in the joysticks a lot. So there's a parallel here that moves up and down, and this moves side to side. Here's something that might confuse you a bit. It looks like a little tower. Here the two flexures are no longer parallel. They are slightly at an angle. That means that as this mobile part moves left and right, it rotates, but it's calculated this time. And it's calculated so that the end here, where these two parallel lines meet, this stays almost put. There's a little bit of movement here because the geometry isn't perfect, but with this you can get a rotation about a point that's outside the hinge. Do you see? Here is solid, but this piece and this piece remain in the same relation. You can't push on here to turn the mobile pin. Instead, if you push here, it will yield to you. But if you push here, it's totally solid. It's really confusing to play with your hands. And this is used in the bottom of my joystick. And this is not my design, but here is going to this next dimension where you are building up flexures all with basically this sort of design here, but where the flexures were parallel before. So what I mean is that these lines, these walls, they were vertical always. This time they aren't vertical, they're actually meeting at a point here, which means that if you keep this point solid, the end of that pen won't move because all these flexures are meeting at a point at the end here. This is a bit outside of the scope. I actually don't know how to design these, but I wanted to show you that if you have one primitive flexure, which I have here, you can build up from there and make many different ones. All these designs that I've shown you that I've designed, so the joint cone and the joystick, they're using just these built up hinges or mechanisms, I should say, based on my flexure primitive. There is an X hinge, there is an outside hinge, and there's an XY mechanism here. For the pen holder, all you have is one parallel linear movement using the doubly linear parallel flexure joint. And for the joint cone, again, it's a XY joint and then some parallel movements. That's it. All of these are made with the primitive and these intermediate built-up phases. Okay, some extra tips. As I've told you, 3D printed flexures, they yield easily. How to stop that? Well, built in some end stop. So you can see this member down here that's dangling down, it hits those two ends. And it's designed so that the flexures never go close to where they would start to yield. I have as my rule of thumb 5 millimeters of displacement at the end of the flexure. Same thing with here. These chompers at the end, when they chomp down, they stop the flexure from moving. And these half circles, if you're compressing it, those will meet. They aren't meeting at normal use. They only meet when you compress it. And that stops the user from flexing those flexures too far. With that, you can have very long-living flexures. And here is another maxim, other rule of thumb that I have, which is never to leave these flexures under tension. So in this mechanism here, where you had the rubber band, or in real world you often have springs that are loading a part. Perhaps I should use the trebuchet here as an example. Don't let the user, or don't let your design be under tension like this for long. Flexure springs should only be used for temporary loads. For easier printing, you might have been wondering what these notches are on all my designs. I call these seam attractors. You can see in the screenshots, if you have this sort of notches on the inside of this sort of parallel mechanism, many of the slicers that you might use, here I'm using Prusa slicer, it will start the perimeter lines on this sort of sharp corner, instead of starting them near where the flexure wall starts, as you saw earlier. So this flexure doesn't have these sort of seam attractors, and it doesn't have the little fillet that's also important, and the line has started near the flexure start, because that's a natural place for the slicer to start its line, because it thinks that's going to be a hidden place. Well, it's going to be a soft spot for the plastic to start yielding from. So always use these sort of seam attractors and the fillets if you can. And further, even better, if you can, instead of starting the flexure out of a wall like this suddenly, make half of it follow another line like this. That's what I mean, extend from a parallel wall if possible. This way the outside lines here, these lines are drawn from this end to this end, and they're going to be very strong. Here, look. How can you have two flexures on top of each other like this? Well, it turns out you can bridge these very easily. Nothing special you have to do, no supports. You can have two flexures cross each other if you're thinking in 3 dimensions. The first line, as you can see, might be a little bit rough, but after a few lines, the flexure print lines, they stabilize, and you can print flexures in thin air as long as you print them vertically, as I've told you. If you must print them horizontally, so laying flat, make sure that you use some sort of slicer trick or something and make them longitudinal like that. I think you can turn the direction of infill in most slicers. I think that would be the only trick. So in my very non-clinical tests, I've only used the very common materials that you can buy on Amazon. PLA Plus has been the most useful. Many people say that PTG should be better for this sort of bending and fatiguing designs and devices, but in my experience, the difference hasn't been big. And if anything, PTG has less springiness. It's more sloppy, so your spring force is not as strong. So it's not even as useful as a flexure as PLA parts, which are more stiff, would be. Here, that's my tips and my different designs. I hope you could glean some out of that. To learn a bit more, there are universities around the world that do research on this sort of topic, but the one with the best publications is here. It's Brigham Young University. They have a whole department for this sort of stuff, and they have great GIFs and videos and even printable STL files that you can find. And next, my next tip to learn an intuition of how these different flexure mechanisms work. I say this unironically. You can search for flexures on Pinterest. Just make sure don't subscribe because they'll send you spam mails every day. And here's one video that I found very useful by Amy Makes Stuff. She made a ton of cool flexure examples and went into the science behind and the calculations behind flexure bending. Right, I'll leave a list of downloadable files for most of what you've seen. And to summarize, use my primitive size, flexure primitive, and build up your own designs from there. It's only a subset of what compliant design and flexures are, but I think if you follow these rules of thumbs, you can get started on designing flexures for your 3D printing projects quite soon. All right, see you again. Goodbye.
Okay, welcome back.
Right.
Hey, Akaki, how are you?
How are you? What's going on?
Not too much. Thank you for tuning in. I know that it's about 3 in the morning your time, so we appreciate you.
No worries.
This hour.
No worries, of course. I hope you've enjoyed the little pre-recorded presentation that I did. I had to cut a few things out, and I had to skip a few things. I had a lot of trinkets and cool mechanisms in my box here to show everyone, but I had to get through all my material. I hope it was quite understandable.
Yeah, no problem. We've got a ton of questions, so I hope that you are awake and ready for some of these.
No worries, of course.
Okay, let's see. I'm just trying to figure out where to start because I believe some of these questions you have answered in the presentations. I'm just going to start at the.
Yes, I was looking at this as well. I can go on this list that I have in my window here as well.
Sure.
I have not tried this with SLA. So SLA is resin printing, as many of you must know.
I have only recently got a resin printer, but what I've understood and heard and experimented with that material, I don't think the brittleness of a resin print would be very good for at least this type of flexures that I'm doing. That would be the answer to that.
Okay. Shall I throw you some questions, or would you like to choose? If you do choose the question, please just say the question asker's name and the question so that people will be able to follow.
The previous question was from Coleman Baker. Thank you very much.
Okay.
Oh, Rob Goblin also asked the same question about TPU, which is the rubbery material that we can print with our FDM printers. And I have not tried these designs that I've designed with TPU either, but I do not imagine that would be very useful either, because it's simply too bendy. It's rubber, so compliant design and flexures. Flex is one part, but you also need that stiffness in there, because a flexure is something that flexes in one dimension but is rigid in the others. And with TPU, I don't think you could get that, at least with the same designs.
Okay. And I see Mikhail has also asked about PTFE and ABS.
Yeah, so these ones I mentioned in the presentation as well. I have tried these. I did not find a big difference. So my philosophy would be to do it with PLA, which is the easiest to print, and it's the most universal, where if you happen to share your design, others can also enjoy it. Maybe if you get into a point with your design where PLA won't cut it, then try the more difficult ones. I would like to ask everyone listening if you have access to, I believe nylon is one of the more exotic filaments lately that people are trying out. I don't have a printer that can print nylon, or I don't have experience with that. That I hear might have more favorable properties, but it's a bit too exotic for me at this point. It would be interesting to know if someone has tried with nylon.
Okay. There is a Nadja who has a fairly complicated question. I don't know if you see that in the window, but would you like to tackle that one?
Can you say the name again?
Sure, Nadja. I can read the question if you like.
Yes, please.
One of the bigger problems I encountered with flexure experiments was that, for example, very thin flexures, like 0.3 millimeters, the actual sizes are different in the CAD than in real life, so there was a lot of trial and error. Moreover, for more complex designs without a dual extrude, I need to glue parts together, which makes the difference from CAD to real life even worse. It would be nice to hear whether you encountered similar problems, and if so, how you addressed them.
So perhaps Nadja is trying to print flexure designs that are meant for some other production method, because I wouldn't myself try to print something that thin. And if you're ending up gluing parts together, then also well, all I can say that I haven't had that problem, because I've designed my designs always with printability in mind first.
Okay.
So, I don't know. So, but the dimensional issue is definitely something that I already mentioned, where if you want to make a wall that's less than the width of one nozzle, indeed less than 2 nozzle sizes, it gets difficult for our slicers and printers to replicate. And that's why my flexures are based on the 0.75 millimeter primitive, exactly.
Okay.
Oh, she asks if I've ever used dual extrude. I haven't done that, no.
Okay. Ben asks, do you have any spiral primitives that you developed that work around some of the typical 3D printed drawbacks?
No, I don't think I've tried. I've printed. I remember printing a spiral spring in from someone else's design, but spiral springs are most common use that I would see for those is to preload something. So this design that I found was maybe you've seen it as well, but it was a loaded box that would open up when you push a button. But this is now doing exactly what I wouldn't recommend you do, which is preloading that spring for a long time before it, so that it would be ready to open, and that would experience that creep problem that I warn against.
I believe a lot of these questions you did answer during the presentation. Perhaps the questions were asked before you got to that part. Alex is asking a question that I think I might be misunderstanding. So the seam attractors that you drew, those are just notches that you draw into the surface. But Alex asks, can you explain more how the seam attractor works in the CAD process?
So when you're designing it in CAD, it's the simplest thing. You simply make any sort of notch you want. The point is to make a sharp-edged notch on a wall, so that your slicer will be attracted to start the perimeter lines at that point. And I know, and many of you also know, that you can also paint on the seam in your slicer manually afterwards. So in that case, you wouldn't need these attractors. But I'm trying to make my prints easier to print for everyone without having to mess around in the slicer. And for that, I recommend adding these sort of notches. Anything with like a little bit of contrast. The slicer will put the weak perimeter line seam there instead of near the flexure.
Great.
Nothing special about that when you're designing the phone.
Okay. And Tony asks, would injecting a high yielding resin into the infill of the part post-print work to increase the life of the flexure?
Well, these flexures that I've designed are also thin that you wouldn't be able to inject anything in there. If you're ready to do molds and injections, then I would just recommend you make everything out of injected and molded parts. My learnings and my designs here are overcoming these shortcomings that FDM, pure FDM parts have. And molded parts would be better in almost any way, I believe. But more work to make, of course.
Yeah. Well, I think it's a sign
infill percentage doesn't matter because they're just walls. Coleman Baker.
Oh, sorry, there was another question, I guess. Okay. Well, I think it's a sign of a good presentation that every question somebody asked, you had already answered by the time the presentation was over. So people, you still got a couple minutes left if you got anything you want to ask Akaki that he's not covered yet.
There's other types of flexures that I never got to. For instance, this is again from the University BYU that I mentioned. It's against what I've taught. It's a flat piece that you can print on your bed, and then it folds up like origami. And they're like pinchers.
Wow, that's cool.
Pretty cool. Yeah, I had a lot of cool things to show, but just look around online. So what I meant at the end when I said go on Pinterest, what I meant by that is there is tons of research on flexures and mechanisms, but as I tried to say, they're often for these micro machines or they're for metallic parts. So they don't translate directly to our 3D printed world, but you can learn a lot of these tricks and the simple machine sort of thinking of flexure mechanisms from just those gifts that you can find online.
Okay. There's a question for Ben about 3D scanning. Do you 3D scan or tediously measure your controllers to design around?
I don't have a good 3D scanner, so I have purchased a very good file of the DualShock controller. I haven't found a good scan online of all the other controllers, so I've exactly done that. I've tediously measured them and then molded my CAD around that measurement.
Okay. I'm struggling to find a question you did not answer. I would be interested, Edward Haynes asks, I would be interested in what sort of applications have you tried outside of game controllers?
Well, these are the most practical ones that I've come up with, but so no, nothing that I can say that I've outputted really. I guess over these game controllers, I'm most proud of that small thing that I showed in the beginning of the pen holder. I think that's the smartest design I've ever done, and it's only one piece, and it took me 10 minutes to design.
Okay.
Because as you see, the beauty of it is that it's replacing 3 parts with just one monolithic object.
Yeah. And you had mentioned the ephemeral nature of these parts, but I see that there's a question from Henry about how long, how many cycles these can go through. Have you ever had anything break in the time that you've been making flexures?
No, so I've had these joysticks on my wall, and I've played around them, made extra videos of them, taken photos of them for over half a year, probably close to a year, and I don't see any sign of them breaking down. But still, that's only so much time, so I can't tell. I wouldn't imagine that they would last for years and years, but I think you would be surprised as long as you do the end stops, so you limit the movement that they experience.
Caleb says, "Oh man, I wish you would have told me you didn't have files for the controllers. I could have scanned."
Oh, hello, Caleb. Yes, I know what he's talking about. He was the one who initiated me making the one-handed controllers.
I see.
Yes, there are a lot of yes. This is something for everyone who's thinking about designing something around game controller specifically. So we're moving a bit off topic, but don't believe any of the 3D files you find online. 90% of 3D files of game controllers are made for visual renders and for visual use only. They aren't true to the actual dimensions.
Interesting. And Tim asks, do you have any tips on how to design flexures that lock in 2 positions like a switch, overcoming a dead point, if that makes sense?
Yes, so there is one design from BYU again that is exactly that. And this, I don't think there's anything special to this. Although I would say that if you take a look at this design, you'll find it on BYU, try and use longer flexures than they do here. So again, this design is definitely made for laser cutting Delrin or some other plastic, and not for FDM printing. It's only accidental that you can kind of start with it. But so this is a very cool design. But they're using this sort of non-3D printable sort of flexures where they have this fat part in the middle and the bendable part is very thin. And you can perhaps see that it's already starting to fatigue.
I see.
But the basic geometry of this, if you made these flexures longer, as I recommend, like maybe 40 millimeters, in either of the 2 stages or the positions that this can end up in, they aren't under load, as I warn that you shouldn't put them under load. So there's nothing problematic about this sort of mechanism if this is where you want to start from. Yeah, bistable mechanism, exactly.
Okay, that's great. And Akaki, oh, by the way, when I was saying your last name, I realized I don't really know how to pronounce your last name. How do you pronounce your last name?
I'm called Akaki Kuumeri.
Kuumeri. Okay, well, I'm sure I butchered it. Is there anything you want to add before we wrap up?
If you want to see more of my cool projects, just go on my YouTube. That's the only one I wanna mention there. And I guess if you want to message me, you can find my email on my YouTube about page as well. That would be my preferable way if you want to message me.
Okay. Well, our great thanks to Akaki for providing all of the hard-won information. Attendees, please do check out Akaki's YouTube channel. Most of you probably seen it already. If you haven't, it's Akaki Kuumeri, Kuumeri at YouTube. Also, check your email inboxes in the next 24 hours because Akaki has sent in a summary of the presentation and some downloadable files that you can use as reference material And we're also going to send you a link to this video so that you can watch it again for reference. And lastly, keep your eyes peeled for next month's Core77 Crash Course, which is going to be on renderings, hosted by rendering expert McKay Nielsen. That's going to be, I believe, mid-May. Watch core77.com for the notification. So thank you again, Akaki. I hope that you get some sleep. Otsukaresama. Thank you.
Otsukaresama. Thank you very much.
All right. Have a great week, guys.